Okay, Assalamualaikum and good morning. So welcome back. So I think let me just go to the notes. Let me enlarge this. Can you see the notes? Okay. I've updated the first lecture, the notes for the first lecture. Why is it not moving? Okay. Because I added a topic which initially I thought it was going to be the second lecture, but I think it fits into the first lecture. And essentially the one that is still on Putra Blast is the old version, so I will update this probably after the lecture today. Okay. Somebody coming in? So let me try to recall where we left from the first lecture. Hopefully there's no instability of the faculty's Wi-Fi today. So please let me know if if I get disconnected again. Right. So where we left off was actually somewhere at functions of state, right? So essentially, okay, the idea is now to be able to find some equations that involve some state variables. Okay, so this we have seen, for instance, for the case of your temperature previously, we know it's going to be a state function of your pressure and volume. Okay, so in other words, this would be what we call a state function or function of states. Okay, and then depending on the equation of state, which is actually the form of the function of f. Okay, usually for the case of ideal gas, you know what it is. Okay, but it can be much more general than that. Okay, so the fact that the variables, if you really think what it is, just check. I hope everything's okay. The variables here, there are three variables, for example, in the case of this ideal gas that are interrelated to each other. But which one do you write as the independent variables, or which one do you write as the dependent variables is really up to your choice. In this particular case, we write P and V as your independent thermodynamic variables, and your theta becomes dependent. But you could actually change them around. Okay, so in other words, over here, one could essentially write your theta and V to be your independent state variables, and then your P will be your did I say independent? Yeah. Theta and V is independent state variables, and P would be your dependent state variables. Okay, and similarly, you can convert it for the case of where V is your dependent state variables. So, of course, all these functions will be different then. Okay, so in the case of, for example, the case of the ideal gas, we already know that the isotherms are given by PV equals to constant, and in fact, when you use the gas temperature, for example, we know how it's related. This is in the case of 1 mole, I think, if I'm not mistaken, n equals to 1. So, so you get your theta g equals to PV over R. So in other words, it's this is just your function, capital F previously. And if you include the number of moles, then this will be the one that's probably familiar to you in high school. you get PV equals to NR temperature, theta G here. Okay. I think the auto admit should work by now, so probably I'm not sure what happens previously. Okay, so besides ideal gas is the simplest that you can think of. Okay, you know what the conditions of ideal gas? You have the gas molecules to be non-interacting, non-interacting, and then they are moving freely. But realistically, you know that's not going to be true. Okay, so for example, we know there is already an equation that you probably have learned somewhere, the van der Waals equation, that takes into account of all these interactions, and also the fact that that the gas molecules or the gas particles actually take up some space. So this is the van der Waals equation. So over here you can actually see there's this constant A here and a constant B here, which is really can be determined experimentally. Okay. What is the constant supposed to be? Your A represents some kind of the intermolecular interaction there. Okay, and then your gas particles, your B is the one that sort of take up the volume of the gas particles. Okay, so you minus the volume of the vessel, so to speak, minus the volume of the gas particles themselves. Okay, so this would be a more realistic equation. Of course, even this you can actually modify it to include other things, but this just to show you that it can be much more complicated. And then if you try to write your function over here, you can see that it's going to be much more. Here your V, for example, appears in both this bracket and this bracket. So it's no longer like theta equals to PV, this kind of thing. Okay. So generally, how your functions going to be, again, we are sticking to the case of what we know from ideal gas. Your function of state will be some function of two variables, two variable x and y, where x and y is probably v or theta or p. Okay. Then you can actually try to learn generally what should be the behavior of these state functions from just simple calculus. Okay, so for example, if you want to see how the state functions changes with respect to the independent variables, you know how to take, for example, the differential of the function itself, and then this would be the partial derivative of your function here. Okay, sometimes, okay, this is actually trying to be a bit more pedantic in the sense that I differentiate this thing, this G and this G. The G, the small g here, denotes the function. This G could be the dependent variable earlier. Okay, so I'm differentiating them between each other. One could even write, identify it this way if you want to. Okay, there's no problem with that. Okay. So if you try to write the infinitesimal change of that state function, then you can use what you know about partial derivatives and then your infinitesimal change of the independent variables. So in this case, for example, you have your partial derivative of small g with respect to your variable x times dx, and then partial derivative of g with respect to y times dy. Okay? So generally, this is what we expect if your state functions are essentially at least continuous, or maybe not just continuous. First derivative continuous at least, then you expect this to happen. But generally, what's given to you is something like this. Okay, you are given a function of x and y times dx and a function of x and y times dy. Of course, you would expect that if this is actually a true what you call differential over here, then you would identify your function a here to be your partial derivative of g with respect to x, and function b here to be your partial derivative of g with respect to y. When that happens, then of course you know that this behaves like a proper differential. But there are more things to consider. For example, if you consider that your state functions have to have higher derivatives, then for example, you want the state function to be smooth, for example, okay, then you need to define higher order derivatives, like your second order derivative. Then you expect this to happen. Oh, I've forgotten to mention the other thing. This is an archaic notation. You can see the way it's being written here. This is normal in thermodynamics. This thing with a bracket with a small y here, that means y is kept constant, and this bracket with a small x here, that means x is kept constant. But essentially, in this particular case, you know that this is what happens when you do partial derivative. Okay? So that's why I call it an archaic kind of notation, but sometimes knowing what is kept constant is actually helpful sometimes. Okay. So in this particular case, for example, then you have second order derivative of g with respect to x twice, okay, which is equal to the partial derivative of x of the partial derivative of g with respect to x earlier. Okay. So this, of course, this is just ordinary calculus, and of course you can also take a partial derivative of g with respect to two different variables, second order, yeah, and then you find that this is going to happen. And you can see this subscript here is now different now, okay, because of the different derivative that you are taking. The first one is with respect to y, you keep x constant. The second one is with respect to x, then you keep y constant. Now, the properties of partial derivatives require that when you do mixed derivatives, d dx, d dy, for example, you must have the property that is equal to the d dy, d dx. Okay. So in other words, in terms of the earlier function, then you need those functions to behave in this way. Okay. Forget that. Forget, for example, that you do not know really this one, but if you observe this, then you know that this is actually the condition of the second order derivative. Okay. So that's why sometimes it's good to consider a slightly more general notion, and then you'll be able to see, okay, what is the condition for the second order derivative? Then you need this one. Okay. So in other words, here you can think of a and b to be some initially arbitrary functions, but then if it satisfies this, then you know that it satisfies this second order differentiation condition. Are you still there? I'm just worried about the Wi-Fi. Okay, please shout. Okay, right. So writing this as a differential one may ask, can you find G itself? Meaning, if we take the G, let's go back. If you take the G here to be equal to that, how can we know whether we can actually find out what this capital G is? That means you actually integrate it. Okay, you integrate the G, you get capital G. Okay. So, okay, in this particular form, you probably would not see it directly, but okay, you have done maths method, right? Everyone, may I ask, have you done when? When do you do maths method? This semester. Pardon? Sem 3. You're in Sem 5. Okay, great. Okay. So that means you know much more. Right. So in this particular case, how do you know that when you want to be able to integrate, then your dg here no, is known as an exact differential, and how can you test whether that's whether that is an exact differential? Well, we have the class on vector calculus before. You can write your g in terms of this vector, for example, and then your dx and dy are written in terms of this vector dr. Okay, so in other words, the g in the scalar form is actually g dot dr. Okay, and what we know is the fact that if this can be is actually exact differential, then you know that one can apply Stoke's theorem. Okay, and in this particular case, the Stoke's theorem is a bit more specialized because there's only x and y, what you call independent variables. Then remember that the Stoke's theorem relates between a line integral and an area integral. So area integral, usually you think of it embedded in three-dimensional space. But now what happens, the three-dimensional space, the area here will be having something like this. So you have an area here, and then the normal to this will have to be pointing outside the x and y plane, okay, because this er is actually denoting in the xy plane. So this will be in the normal to that surface will be in the direction of z. Okay, so if I want to integrate this, then I will just take the z component of that. Okay, so curl g, the z component of curl g will be given by that. Okay, and what does that tells us? Well, we have this condition earlier. If this is actually true, okay, db dx, well, partial b partial x equals to pi, which is precisely what you have here, but being taken the difference between them. So here partial b partial x minus partial a partial y. If this is actually an exact differential, then this will cancel out. Okay, so in other words, what we have over here is that this thing will be equal to 0, right? Or if you think what it is, this is just taking what you call a loop, okay, around certain loop here, for example, okay, and then what you can try to do, I can break it out into two parts. There's path 1, and then there's another path 2. Okay, so that loop integral are now broken into two paths. Okay, so here is from R1, say this is say R1, this is R2. So the first one is going from R1 to R2. Okay, so you integrate in path 1, so this will be path 1. And then path 2 to circle it back into a loop. Okay, this will be path 2. Then it will be integrated from R2 to R1. Okay, so that gives you the closed integral. We should now know that must be equal to 0. Implementing this means you get a exact differential. Okay, and what does that tell us? Okay, that tells us if I bring say this onto the other side of the equation, for example, then I will get a minus sign for that, and the minus sign I can flip these two limits, then I will get this condition, okay, which says that if you take the integral of g dot dr, which is your dg previously, okay, between 2 points, then it's going to be independent of the path. Okay, so meaning over here in this diagram, I can take this path or I can take this path. So this path 2, this path 1. Okay, with now the corrected what you call limits, okay, from R1 to R2. So that tells us, okay, generally what happens in this particular case, if you are able to do this, then in other words, one can actually write this as a function of state of, well, as a function of x and y, where you fix a particular limit for this, and this will be your point xy. Okay, and that makes this as a function of x and y. Okay, what else? Okay, another point. Actually, no, it's not really necessary. But so once you know that this is independent of path, of course, what can it depend on then? Well, it can depend on the what you call the endpoints. So this is essentially the argument that, okay, in the end, what's left is the resultant should be dependent on this endpoints r plus dr, or r, or in general r1, r2. Okay, so in other words, you get back to the same concept that your state function has to be a function of x and y. Okay, and now this is the general case. Then this should be true for all the thermodynamic variables. Okay, so I hope that's where the old version of the notes stops, but we want to go to the example of the state functions that you already know. Okay, so the first one would be what we call internal energy. Now, internal energy is just like what it says. That means you can have a system storing some kind of energy. Okay, so the one that should be of interest to us is it's done in the book. Okay, you can read up the history of this. It's Joule's paddle wheel experiment. What it does has this so-called set of weights on the pulley, and then wound up with this mechanical system, and then this system has paddle wheels where the container here contains some water. Okay, so what happens is when this weights drop, this thing gets rotated, okay, and then the paddle wheels sort of gush around the water, and you'll find that there is a change in temperature. There will be a temperature rise. So you change your potential energy mgh to no, in a way it's giving you the rise in temperature. Okay. Perhaps much more common these days is to consider electrical work instead of mechanical work. What do? You use your heater, for example. In my student days, I use a bare heater, no, to cook Maggi noodles, for example. Okay, so you pass electrical current through your electrical coil with certain resistance and heats up, and it changes the temperature of the water. So you have two different versions there. Essentially, one with mechanical work and the other is electrical work. Of course, no, to raise the temperature, one could just simply heat it up. So the main idea here is all these three different modes of experiment. If you compare each experiment and with the same rise of temperature, that means you can quantify how much heat is involved in raising a particular volume of water. Okay, and that just implies that heat is just the same as mechanical work, which is energy, and or electrical work, which is also energy. So in other words, that is just what it's trying to do. But more than that, one could start thinking of raising the volume of water to a certain degree of temperature by using different mixture of experiments. Okay, so you can mix up your mechanical work and electrical work, and it doesn't matter how you mix it up. If you want it to raise to a certain temperature, you can do whichever way. Okay, the amount of work that's being done is just the same thing, the total work. Okay, so what's really important is the initial state of the water, in this case the temperature of the water, for example, and the final state of the water. Okay, so that means if we want to raise it to a certain final temperature, then you need so much work to be done. Okay, so that's the main idea about that. So the fact that one really has this idea of energy being put in, okay, your mechanical work or your what was the other one, electrical work, or you input heat directly, okay, says that okay, the capacity of the system to store energy from there. So how can one know, because they are supposed to be independent of each other, so it doesn't really depend on which way that you do it. Okay, you always raise the temperature. So one can define a slightly abstract quantity called the internal energy. Okay, so you can write your internal energy as a function of state variables. So you can choose whichever two that you want. You can put pressure and temperature, or volume and temperature, or pressure or volume. Okay, doesn't matter. Okay, and of course you can also have some reference value. So here is just, it's not so important, but the one that's going to be important to us is the change in your internal energy. Now, the idea of the first law of thermodynamics is to actually use heat as part of what you call the energy conversion. Okay, so in other words, energy can only be seen to be conserved if heat is taken into account as a heat energy. Okay, so in other words, any change with respect to the internal energy is given by the work done plus your heat energy. Okay. The alternate statement is like what I mentioned before. You can actually convert this heat or convert this work and be stored as an internal energy of the system. Okay, that's it. That's the additional section of lecture 1. So maybe I should pause at this point. Are there any questions? I hope I'm still recording. Yes. Everyone's okay? I'm sorry that I didn't upload the notes, updated notes yet, and also the lecture 2 have also not uploaded it. So I will do this after the lecture. Anyone wants to say something or comment or questions? This is a good time. Okay, otherwise we just continue. So this is lecture 1. By the way, you probably see that I'm doing things bit by bit because I don't have a ready set of notes for statistical mechanics. Okay. In fact, within the recent history, the last time I teach statistical mechanics was the last 2 semesters, and I used a different book, which is a hard book, because they want it to be the most up-to-date book, no, the most recent book. And I use that. It's not so helpful for students because it goes very very advanced. So that's why I returned to this particular book, which is, I think, the easiest that I can find. Right. So this second lecture is on reversible changes, and then we introduce another state function called enthalpy, and then related enthalpy is going to be heat capacity. Okay. So the first thing to do is to understand the idea of reversible changes. So here is a system of well, it's a gas system contained inside a cylinder with a piston on top. Okay, so this you can think this of this system is now in equilibrium. Okay, there's a gas inside here. This mass is supposed to exert certain force on that, but now they are just in equilibrium. Okay, now if you add further mass to this piston, for example, then you will be able to see that you actually compress your gas, okay, because this is going to go down, and then when you make this piston goes down, then there you'll be able to see there's a temperature rise of your gas. But once you remove that additional mass, okay, you remove that additional mass, then the gas will start to expand back again. Okay, rather than compressed previously, then it expands back and then it goes back to the original temperature. So in other words, you can change the state of the system, but then you are able to restore the original state. Okay. Same thing if you allow these walls of this cylinder, for example, to transfer heat slowly. Okay. Then what can happen if you think of heating this thing slowly, then you find that this gas will expand, and of course the temperature is going to rise because it's being heated. Okay, and then if the gas cools down, so you remove the heater, for example, and the gas cools down, and then it will return to original volume and temperature. So in other words, this is another case where you have initially there's a change in the state, and then it goes back to the original state. So in such cases, when you are able to do that, those processes are called reversible, or you can think of a reversible process as the one process that, okay, spelling mistake here, reversible process is defined as one that may be reversed to bring back the system into the original state, okay, which is what I said earlier. And by saying so, you probably have noticed, for example, in life, not many things are reversible. Okay, there are many things irreversible. Okay, for example, if you break a glass, you don't expect the glass to form back again. Okay, so that things, those kind of processes are irreversible. Okay, but those are actually very complicated things. So sometimes we limit ourselves to studying reversible processes. Okay, in fact, people still do not really understand irreversible processes that well. Okay, so in differentiating between these two, one needs to take note of few things. Is one is that there are two different time scales. Okay, there are time scale of the processes of, say, of the gas molecules, for example. Okay, the microscopic processes, and the time scale where you start to observe the whole macroscopic system. Okay, so if you think of the system at the microscopic level, you can see that the gas molecules are actually doing a lot of things. There are a lot of rapid changes at that microscopic time scale, and usually this time scale are given by the collision time between particles. Okay. Now the observed macroscopic system usually have a slower variation, and you expect the time scale to be much greater than the microscopic time scale. So when we go for equilibrium state, for example, usually it's actually you know this so-called microscopy is processes going all the time. Okay, but the fact that if you compare the two time scales, you expect that the tau c here is the collision time, different taken the ratio with respect to the observation time. Okay, then this is going to be very small. Okay, so in other words, your equilibrium state is actually making this approximation of your what you call your what happens at the microscopic scale and what happens at the macroscopic scale. Okay, so if there is an equilibrium state, usually one thinks of this, okay, it's within this order of this what you call when you do a measurement, there's some kind of you know that this is accurate to a certain error, for example, then this equilibrium state is actually given in terms of this particular order, and this is very small. Okay, then if this is actually very small, then if this is actually a reversible process, then if this is a process that you want it to be reversible, this can be maintained as long as this is this is actually small. Okay, usually what happens is that there are differences between I didn't mention this before that. So we have the reversible process, and then we have the gradual changes, as if that the system is going to be remaining in equilibrium at each point when we observe. Okay, and this is what we call the quasi-static changes. So the quasi-static, the difference between quasi-static state and the equilibrium state is when we consider that, okay, you can ignore certain things happening. So in this particular case, you actually ignore certain dissipation of energy, and when you ignore this dissipation of energy, of course, within certain error scale, for example, then of course you can talk about reversibility. But if we do not ignore this dissipation, then of course then you get your irreversibility. So it's a bit philosophical in this particular case, but no, you have to be aware. Okay, the essential idea is you have to be aware of the two different time scales that you have in the processes involved. Yeah. What does the now? It's just saying that no. For example, how should I do this? When you try to see when you do an experiment, uh, you normally ignore what happens at the what you call it, at the atomic level, so you don't care what happens at the atomic level, but at the observation level, then you know that okay, I can see this certain slow change being done, but is at some no, macroscopic scale. Okay, so that time scale is that your tau r thing, your observation time scale. Is that it's a bit hard to pinpoint a particular definition for this. No, it depends on the system. Well, okay, so okay, now maybe get some philosophical papers for you to read, then you can review this later on. Right. Okay. Let's consider the case of that another spelling mistake here. The piston cylinder thing, and then you add this tiny delta m, and then what's going to happen from the previous picture? This thing will drops down in height. Okay, so let's do this a little bit more quantitative here. So you have dv equals to minus a dz. The change in volume is given by the fall of the height. Okay, and then essentially the work done by the mechanical work done is given by the total mass m plus delta m times g times dz. So this is just your mgh thing. Okay. Here, okay, maybe I'll explain afterwards. Okay, and then in order to convert it to something that no, we have already used thermodynamical variables as pressure, volume, kind of thing. So I'm going to change this to pressure. So this is your force divided by the area, that gives you pressure, and then your area times your dz will be your volume. Okay. Now there is this notation that I use. It's a bit odd to use this notation. In the book it's slightly different, but here is a cross, a line crossing D here. That is just to say that you cannot treat this as your exact differential like what we have seen before. Okay, so it's just a small quantity, which is not an exact differential. Okay, so if you ignore this delta m, okay, you just simply use your the bigger mass, then you can see that okay, this just gives you dw equals to minus p, which is that, ignoring delta m there. Otherwise you have to put p plus delta p plus delta p there, but just ignore that delta m, so you get p times dv there. Okay, so that would be your mechanical work. Okay, so in order for us to understand what's happening to that particular gas, okay, there will be changes in the temperature, okay, just like what we mentioned earlier. And now if we want to write this down as what's the internal energy, how does it change, how does it relate to the mechanical work, and how does it relate to the heat involved in raising the temperature. Okay, then you have the first law of thermodynamics, which just says that okay, essentially your energy is conserved. Okay, whatever change in internal energy is given by these two quantities. Okay, so this is your heat, okay, and then this is your mechanical work. Okay. So what else? Try to remember what I'm supposed to say. Right, okay. So we have to consider both. Of course, we can take into account different circumstances, but this is what we have in terms of conservation of energy. But now let's look at the mechanical work. Okay, suppose I know that the two the two points that define the state, the initial state and the final state, and that is given by two different volumes, initial volume and final volume. Then you can actually calculate your mechanical work by just integrating this PdV. But remember that this is not really remember that this is d with the cross in the middle. Okay, so it's not an exact differential, but that doesn't mean that you cannot integrate. It just means that it's not an exact differential. That means your integral, you can do the integral, but you find that your integral will be different when you do when you take different path. Okay, so here's a picture, for example. If I use the isotherm thing, so this is between P1V1 and P2V2. Okay, that defines the gaseous state. Okay, I can take the isotherm to give you your first path, but I can also take a different path which is not the isotherm. Okay, so then I will have two different what you call work done there. So this is this path will give you this work done, and the second path will give you the other work done. Okay, the area under the curve, essentially. Okay, so in other words, then you'll find that okay, your work is not really a state function because you have different areas, different work done. Okay, correspond to the different path. Despite that, your two conditions, the initial condition and the final condition, is just the same. Okay, so one has to, okay, what can we do with respect to this? Well, if you have done thermodynamics, what one can actually do, remember the internal energy is actually a state function. So if you try to calculate your internal energy across this loop, then there's no change of internal energy. Okay, but what's remember what is the condition here? Your internal energy is related to dq plus dw, and this is not exact. This is not exact, but this one is exact. Okay, so take for example going through this loop. Okay, so if I were to take it so this is the point underneath. If I were to take this path clockwise, so nowadays you don't have a mechanical clock, you always have what you call digital clock. You probably forget what is clockwise. Clockwise is going from here to there, so clockwise from there. Okay, so what actually happens, you take the area of the under the curve path 2, and then it goes that way. When it goes that way, it goes the opposite way of the path 1, right? So you have to minus away this path. So that area minus this area, you get a positive area. Okay. Okay. This red one is the area under path 2, right? Now the area under path 1, in this way, if it goes this way, then this area is positive. But if we go the other way, set where I go the other way, then I have to minus this area. Okay. So then this one minus that area is a positive area. So here you get area to be positive. And remember that your work done is actually minus P dV. So that means this is positive, so that means your work done is actually negative. So what does it mean by a negative work? Well, it means that the system is actually doing work to the surrounding. Okay. So what about anti-clockwise? So anti-clockwise would be going the other way around. So this would be going this way. Okay, this is anti-clockwise. Okay, this is clockwise. So if you take anti-clockwise, then what you do, you take this minus that. So you take this area minus that area, that will be negative. And we will use this formula, then your work done is positive. So work done is positive, meaning that work done is on the system. So what does it mean by work done on the surroundings and work done on the system? Well, work done on the surrounding, that means it loses energy. It loses in terms of heat, for example. Work done on the system, that means the system gains energy, the heat energy. Okay. So once you include this both contribution of heat and work done, then you get to the idea of your internal energy. So heat gain and heat loss, that means inclusive with the mechanical work, then you essentially get no change in your internal state. Internal energy. Sorry, I have a class now. Right. Where was I? Maybe I should pause there for a while and see what's going on. Okay. So let's take a break. Okay, let's take a break. Let's take a break for 5 minutes. Is everyone back? Doesn't seem so. You think we can start? Okay, great. Right. So going back to we want to do a little bit more quantitative kind of thing. So we need to have a proper equation to write down. So one thing that we can actually do is to consider the case of the ideal gas in a reversible process. Then I can consider what we know about ideal gas, for example, is given by that. Here, this is the equation of state. Then I can plug this into the equation of your dW, for example, and then Okay, so that means I have your dv here from there, and then I have your p is actually equals to that, so I have your v at the bottom. So I can actually do some calculation to see, okay, what is the mechanical work being done when you go from certain state of v1 to v2. Okay, so so that gives you this log kind of function. But for irreversible process, then it's going to be a bit more complicated, because then your dw will not be equals to minus pdv, but instead what's going to happen is that your dw is greater than minus pdv. Okay, usually this happens when you have large changes, so that means over here, instead of your delta that the small delta that previously we had, this is going to be a finite change, so that usually can incur some kind of irreversible process. Okay, right, and this idea of doing connecting internal energy and work is not limited to mechanical work. So you can start to think of other kind of processes, like things inside magnetic field. Okay, so you can talk about work by magnetizing a system, or inside electric field, work by electrical displacement, or you can think of it in terms of surface tension. Then you can talk about no, work done by changing the areas of the surface, for example. So, but those probably, when we get to that, then we introduce all these things again. Okay, at this stage we are just revising the notions of thermodynamics that we have actually learned before. Right. Okay, the next thing to do is to talk about enthalpy. Enthalpy is another state function, which we shall see in a minute. And in the previous course that I did for statistical mechanics, last two sem, I introduced a different idea. Okay, maybe just for your understanding, sometimes these state functions in different books, internal energy and enthalpy, for example, sometimes are actually what they call thermodynamic potentials. So sometimes different books will give you different terms, but it actually means more or less the same thing. Of course, they may have a different intent when they use potential, for example. And then what else? There was, yeah, okay. Going from internal energy, say U, to enthalpy, in the previous course, there is a mathematical process called Legendre Transform. Have you heard about Legendre Transform before? It's either yes or no. Have you done classical mechanics? Also not yet. Okay, great. So that means, of course, you do not know then. Legendre Transform is if you have done classical mechanics, there are two modern versions of classical mechanics. The old one is Newtonian mechanics. Okay, the Newtonian mechanics are what we call it's like thermodynamics. It's what we call an empirical kind of study. Okay, because your Newton's law are all coming from what you call experimental observations. But there is a modern version of it. No, if you have not done it, then you probably it doesn't make too much sense to you. But later on, probably when you do it, there's what we call a Lagrangian mechanics. Oops. Lagrangian Mechanics, where you use Q and Q dot. Q is your position and Q dot is your velocity. And then you change it to what we call Hamiltonian Mechanics, which is a function of Q and P. And the changing of this Lagrangian mechanics to Hamiltonian mechanics involve what we call the Legendre Transform. Okay? The same thing actually happens in thermodynamics. You can actually change the state functions in a way that you change the variables involved. Here is Q and Q dot, here is Q and P. One can actually do also differently for the case of the thermodynamics. Okay, so you change your state functions. In a sense, it's involving a change of your state variables. Okay, but okay, I mean this is not just something extra that you might want to keep in mind. Probably when you read a different book, you will find it. Okay, let's go back to this idea of this increasing of the volume of the system to do work on the surroundings, and there will be a change in internal energy. Okay, this, for example, in the case of increase in volume, for example, over here, you go to that volume. Okay. So if I don't do it in a cycle, there will be change in. When you do this, there will be a change in internal energy. And the change in internal energy must be given by the first law of thermodynamics, which is, where does the change come from? Well, it can come from the heat, or it can come from the mechanical work. This is your TW. Now, what happens is that, okay, I can just simply invert this equation to get, again, a lot of spelling mistake. I'm trying to finish out earlier this morning. Heat added to the system at constant pressure, for example, then I will be able to rewrite this to put this PdV on the other side, and then I get your amount of heat given by du plus PdV. Now, if it's a constant pressure, then I can bring your P inside your differential, and I get U plus PV. Okay. Why you can do that? Well, if you take the differential of dPV, I'll get what? I'll get first dP times V plus P times dV. But P being constant, then dP will be equal to 0. Okay? So in other words, with this, I have this thing added up, and remember that this is a state function, and the thing that you add up is really another state function, P and V. Okay? So this you define as what we call the enthalpy. And we denote this by H, almost, I think, when I first learned of it, I think of H as heat, but it's enthalpy, okay? So, but in certain circumstances, it is what we call the heat energy, okay? To understand this better, you take the what you call the differential of this enthalpy, because remember that this is a function of state. So your dH will be an exact differential, but what can happen is that when you do the differential of the whole thing, then the individual things might not be the exact differential. Okay, so in this particular case, you get essentially you get du, and then you get dPV plus PdV, and then remember that du plus where is it? So I have du plus dPV, and then this will be Control Z, and then this will be plus du. Okay, so du plus p dv, okay, these two together is your dq. Okay, so I get dq, so the one that's left out is your v dp. So if I were to consider the case of the constant pressure case back in this particular uh, new state function, then your dH is really your heat, okay, because your dP is 0. Okay. The other thing is, given this relationship, you can also see that I can calculate what is the change in enthalpy by looking at the change of your internal energy. Okay, so you know one of them, you can calculate the other. So here's an example in the book which was initially mysterious to me, but then I have to look up other references because I can't remember some of this stuff anymore. This is essentially chemistry. So there are two forms of calcium. I think they call it calcium carbonate, right? So, and there are two forms of this, which is the calcite and the aragonite. Okay, and suppose you do this at a pressure of 1 bar, which is 10 to the power 5 Newton per meter squared, or Pascal, and you have 1 mole of this calcium carbonate, okay, and you convert this calcium carbonate from the form of calcite to aragonite, there will be an increase of internal energy of about 210 joules. Okay, and from one form to the other, it also changes the density. So it changes from this much of kilogram per meter cube to this much kilogram per meter cube. And it was given in the book, the mass of 1 mole of calcium carbonate is about 0.1 kilogram. So now we want to find the change in enthalpy given this change in internal energy. So we need to find the change in volume. Well, the volume of what is given is the density, the change in density, and then we know only the molar mass, so to speak, okay, of this calcium carbonate. And then what needs to be done is to find out the volume from the case of the calcite to the aragonite, which can do by taking this mass divided by the density, okay, and then you get that. So once you know that, then you see that there's a change in volume. Then you can apply again this formula that we had seen earlier, which is actually dH equals du plus p dv, okay, and then you just substitute the values in, and then you find that your dH or delta H is just 209.7 joules, which is very close to your change in internal energy. So in other words, your PV in this particular case is only making a very small contribution, which is about negative 0.3 times 10 to the minus 5. No, minus 0.3, sorry. Okay. So people have studied that this is at atmospheric pressure. Now people are actually studying how it behaves at higher pressures. And at higher pressures, the contribution of this change in enthalpy can be actually bigger. Okay, so that means you can actually produce more heat from that. All right. With respect to talking about heat now, okay, we already seen that now by adding heat to a system you get temperature rise. So but this will actually depend on the amount of matter inside that system. So there's a much more intrinsic property that one can actually calculate, which is the heat capacity, and this is the ratio of heat added to the given temperature rise. Okay, so roughly this is given by this dq d theta. Again, one really have to be careful about the meaning of this. Okay? Remember that there are two possibilities over here, that you can do this at constant volume, calculate this at constant volume, or you can do this at constant pressure, and they give different answers. Okay, so the one with a constant volume, okay, means you get PdV equals 0. Then what happens then dqV is given by a specific heat at constant volume times d theta. Okay, that is what we call the specific heat, heat capacity at constant volume. Okay, specific heat, I think it means something else. Heat capacity at constant volume can now be related to the change in internal energy from our previous relationship. Then in other words, the heat capacity at constant volume is just the partial derivative of the internal energy with respect to the temperature. Oops, I think I missed an equation here. Try to remember. I think this is actually okay. Here's an example of monatomic gas. So that's good. I haven't uploaded this lecture notes yet. Ideal monatomic gas. What does it mean by that? The gas molecules are just monoatoms. Okay. So when you do monoatoms, they are just like real particles, and the only motion that can take place is just like translational motion in 3D. Okay, but if you have something like a dumbbell, for example, then you can have other motion like rotation and things like that. So that will give you different degrees of freedom. So with translational, then there will only be 3 degrees of freedom, okay, because of the 3 dimension. So there, from kinetic theory of gas, I hope I'm right. Let me just check with the notes. Yeah, I left out that equation. U equals to, U equals to 3 and R theta G divided by 2. Usually it's written in terms of ds3 over 2 and R theta G. Okay, so the 3 here correspond to the 3 degrees of freedom of the translation. So if there are more degrees of what you call degrees of freedom, like the rotation thing, then this could be more than 3. Okay. So once you have your U, the expression for U, then you can actually calculate what your specific heat, again I'm using specific heat capacity at constant volume to be equals to 3 NR divided by 2. Okay. You just differentiate with respect to theta. Well, if you have, instead of constant volume, you have constant pressure state, then you will define a different heat capacity here, Cp. And over here, what's going to happen is the fact that volume can change. Okay, So there's work done with respect to the volume changes as well. So that means the amount of energy to be taken up is going to be bigger in that sense. So not only just to raise the temperature, you need to also take part of the heat energy to go into the volume change. Okay, so in other words, you expect this quantity Cp to be bigger than Cv. Okay, so let's look at the case of again the ideal monatomic gas. So Cp in general will be now given by this, the h d theta here, and then your h is given by u plus pv, so you get that. Okay, so for the case of the monatomic gas, you have that. Okay, the missing equation earlier. Okay, so you take the derivative of u with respect to theta, you get this quantity, but you also have PV here that you need to take into account. PV is given in terms of, say, well, if it's n moles, then it will be nr theta j. Okay, so you need to differentiate again with respect to that, theta. And what happens, then you'll find that your Cp and Cv are going to be related in this form. This is the case of 1 mole. So, so you can see if you rearrange the equation there, you'll see that the difference between the heat capacity at constant pressure and heat capacity at constant volume is just given by the gas constant. And this is the table that was shown in the book. You can see that what's the gas constant? I can't remember the anyone can remember what gas constants? Let me look it up. I can't remember all these things. Okay. Okay. The gas constant is about 8.3, right? So you can see from the table, it's more or less about that. Okay. Of course, the others, because you have more complicated molecules, then you might have some difference between them. Okay. So now, why is this large difference? Is because remember what's the difference between the two heat capacities? One will involve just heating, right, which is your Cv. The other ones involve the expansion of the gas itself. So that the fact that the gas expands significantly, then you really have that large difference. The other thing that was actually not really shown here is if you have more number of particles, then you also have your heat capacity to increase. So you have 2 moles, then your heat capacity will double up. Okay. I think I have one last thing before I think that's all I got prepared today. This is the last section of your first chapter of the book. Is to talk about adiabatic change in ideal gas. Okay, so again we consider the simpler case of 1 mole, so otherwise you have to put n there. So you get PV equals nr theta g. So now what do? You take the differential of that, so you get PdV plus VdP equals to R d theta g. Okay. And earlier we have seen this relationship between the temperature change and the change in internal energy. So you get Cv d theta g. And then for adiabatic change, remember adiabatic change means what? Remember, you have a change in internal energy, you have essentially the heat. plus the mechanical work. But adiabatic change, there's no heat, so your dq will be 0. So the only thing that's left is essentially your mechanical work. Okay, so you have du equals to minus p dv for adiabatic change. So if you combine these two, and then you'll be able to write this equation down, okay, and then rearrange it so that you get your differential of p with the p at the denominator and differential v at the and v at the denominator, and then you have this constant which is actually your heat capacity ratio. What happens in this particular case, you can actually integrate this. Okay, so you just integrate that one, you bring on one to the other side, for example, then you'll be able to get this so-called equation of state for adiabatic change. Okay, which is slightly different from the case of your ideal gas thing. Okay. And if you use this what you call equation of state, then you can also rewrite this in terms of the theta and v. So these are some useful equations that when you do calculations for all these processes in thermodynamics, you'll be able to use these quantities. Okay. So I think I will have to stop there for today because that's all I have. Okay. And that's the end of chapter 1 of that particular book. So any questions? Okay, I know it's too early for you. I will try to put this up and then maybe sometime, no, because we already finished off one chapter. I'm still thinking of how to do the assignments, whether I wait for 1 or 2 chapters or just a single chapter. Okay, then I'll give you an assignment. Okay, but in the book, I think you have seen the book. There are some exercises that you can actually try to do. Okay, so I will take your attendance now. So let me look at the attendance. Okay, I think that's it for today. So thank you very much for listening. Sorry, I have to finish early because that's all I prepared for today. Okay.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Okay.
Thank you,
Bye.
Doctor.
Any updates about assignment or lecture notes or maybe quizzes later on, I will put it in the WhatsApp group. Okay. Okay. Bye.